Hi, this is the mark scheme for question 217, electric field strength. Make sure you've done the questions all the way through, make sure you've got a green pen to mark it, make sure you show your annotations and improvements on the paper in green pen. Part A. An electric field is a region of space where charged particles would experience a force acting on them if placed at any point at a distance from any other charged particles. Part B. Define what is meant by electric field strength. Electric field strength is the force per unit charge that would act at that point if a charge were placed there. Secondly, you also need to mention that it's force per unit positive charge, because the electric field strength is a vector and therefore has to go in the direction of the force that would act on a positive charge. Part C. Calculate the magnitude of the force experienced by the electron. You should get an answer of 5.6 times 10 to the minus 23 newtons. You're using the equation E equals F over Q, which rearranges to give F equals EQ. The force is equal to the electric field strength multiplied by the charge. Part D. You're asked to find the electric field strength at the position of the helium nucleus. So you're going to use the equation E equals F over Q. You should get an answer of 4.7 times 10 to the 13 newtons per coulomb. The force on the helium nucleus is 15 times 10 to the minus 6 newtons, and you divide that by the charge on the helium nucleus. The charge on the helium nucleus is 2 times the fundamental charge. In other words, it is 2 times 1.6 times 10 to the minus 19 coulombs. Part E. Calculate the electric field strength 10 centimetres from a single electron. The answer you get should be 1.44 times 10 to the minus 7 newtons per coulomb. The equation used to get that is E equals KQ over R squared. Q, the charge, is the fundamental charge. It's the charge on the electron. And the distance 10 centimetres from it needs to be 10 times 10 to the minus 2. Don't forget to square R. Square the distance on the bottom. Part F. Calculate the electric field strength at a distance of 50 centimetres from the surface of the sphere. So you need to add the 50 centimetres to the radius of the sphere to give a total distance from the centre of the sphere of 0.58 metres. And then you should get an electric field strength of 6.7 times 10 to the 8 newtons per coulomb. You're using the equation E equals KQ over R squared. Part G. Up to what distance from a metal sphere carrying a charge of 1,000 coulombs might this be expected to happen, where the air breaks down? So you use the equation E equals KQ over R squared. You rearrange that so that R is the subject of the equation. So R equals the square root of KQ over E, where E is the electric field strength. You put in the values from the question and you find that R should be 1,732 metres, or 1.7 kilometres. Clearly this is unlikely. A charge of 1,000 coulombs is actually unreasonably large. If instead you used a charge of 1 millicoulomb, you should find that you get a distance of 1.73 metres, which is much more reasonable. So corona discharge would happen up to that distance away. So mark your work. If you think you could get that all perfectly right in an exam, under exam conditions, give yourself a 3. If you've benefited from the feedback and you've improved your answer, give yourself a 2. If you're still unsure as to what to do with this question, mostly give yourself a 1, and 0 if you think you need to redo the question.